Burp Suite's built-in browser. Burp Suite provides its own native built-in web browser based on Chromium. Let's begin familiarizing ourselves with this tool. After launching Burp Suite, we'll click on the Proxy tab, then the button titled Open Browser. Next, a browser window will open. With the Intercept button deactivated, Burp's proxy will automatically store the requests we send through the built-in browser. In the coming sections, we'll further discuss the tabs displayed within Burp Suite. We can continue practicing the concepts explored in this section by configuring a web browser, such as Firefox, to communicate with Burp Suite over port 8080 via the proxy configuration inside of Mozilla Firefox. Using Burp Suite with other browsers. Before we move on to some of the other tools in Burp Suite, let's demonstrate how to configure another browser to use Burp Suite as a proxy. In Firefox, we can do this by navigating to the Preferences section, scrolling down to Network Settings, then clicking on the Settings button. Here, we'll choose the Manual option, setting the appropriate IP address and listening port. In our case, the proxy and the browser reside on the same host, so we'll use the loopback interface and specify port 8080. Finally, we'll check the Also Use This Proxy for FTP and HTTPS option in order to make sure that we can intercept every request while testing the target application. Note that once we've configured Firefox in this way, we will need to run Burp Suite to access any website. To stop using Burp Suite as a proxy, we must return to Connection Settings and select Use System Proxy Settings. Proxy. Next, we'll explore the Proxy tab. This section of Burp Suite manages the interception of web traffic, which is the core functionality of Burp Suite itself. During our application assessments, we'll switch to this window often to turn the intercept functionality on or off. If the intercept functionality is set to on, Burp will capture all of the traffic passing through the browser. However, if it is turned off, our requests will still be stored in the HTTP History tab, which we can access later. By default, Burp is configured to intercept requests. By directing our web browser to a web page, we'll observe that Burp Suite captures the request inside of the Proxy tab. We can click the Forward button to allow the request to be rendered in our web browser. We have now verified capture inside of Burp Suite for the initial load of the wplogin.php endpoint. Let's turn interception off before we proceed. Now let's click on the HTTP History tab, located right next to the Intercept tab. This tab displays a history of every item and endpoint used during our session, similar to how the browser would store recent searches or visited domains. Let's visit various pages of the WordPress website and review how the history is displayed. Browsing through the site, we can observe how the HTTP History tab updates accordingly. The History tab will sort the pages we have visited and traffic that we forward in sequential order. This column indicates the order in which we visited the pages. In this case, our first listing is the URI of WP Login. We can continue browsing the website and switching between the browser and the HTTP History tab to observe this in action. Next, let's examine the Options tab. There are two important reasons for us to review this tab. First, if we ever need to make changes to the local port Burp Suite is bound to, we'll manage that in this tab by clicking the respective Add or Edit buttons. Second, if we scroll down, we'll find the Match and Replace functionality that we can use when a request is intercepted. This functionality allows Burp Suite to modify requests and responses based on the enabled rules. We can leverage this to render content from the perspective of Internet Explorer, Google Chrome, or Firefox, for example, even mimicking mobile devices. In the next section, we'll explore another tab known as Intruder. Intruder. Let's explore Burp further by clicking the Intruder tab, then clicking on Positions. We can leverage our captured requests using this tab to position our manipulated text in payload word list form at a location of our choice. Whenever we capture a request, every form of input, including get and post data and headers, can be manipulated with Intruder. We can modify our payload position by moving two instances of the section sign characters. Our payload will be delivered between them. For example, suppose we've intercepted a parameter for the login form. Let's enter the username and password input values so that they'll be noticeable during the interception. We'll choose admin for the username. After clicking the Login button, Burp Suite intercepts our request in the Proxy tab. We can right-click in the request and select Send to Intruder to move our intercepted request into the Intruder tab. Clicking on the Intruder tab next, we'll discover that Burp Suite has configured the request for a brute forcing type of attack. Intruder has filled almost all input sources, with the exception of headers, and wrapped them in the section sign character. Any word list payload we select will be inserted between these characters. If we want to quickly clear all of the section sign characters at once and specify that we're only interested in one or two parameters, we can simply click Clear on the right. Once cleared, we can enter two of these characters into the payload position of our choice by clicking Add. Let's practice by targeting the password parameter to attempt brute forcing the admin account. It's now clear where our large list of passwords will be placed in the brute force series of requests. Before we click Start Attack, however, we need to visit the Payloads tab. Let's load a small custom word list to the Payloads tab. We will create a file in our home directory to use for our example. While using Burp Suite Community Edition means our requests will be throttled, we can still leverage Intruder for this attack. We can load any word list we want into the Payload Options section of this tab. For this example, we'll use the short word list we created to demonstrate the output of Intruder. Let's click Load and load our word list into Burp Suite. After verifying that our chosen word list has been loaded into Burp Suite, we can begin our attack by clicking Start Attack. We will receive a pop-up message warning us that our requests will be throttled because we are using Burp Suite Community Edition. We can simply click OK to move forward with the attack. By carefully paying attention to the response size returned, we'll notice that the length of a successful login with the password value of password provides a different response size than the other failed attempts. A successful attack yields a response size of 1097 characters. With the password cracked, we can now log in to the administrative interface for WordPress. In the next section, we will discuss Repeater, one of our most essential tools for performing web application assessments. Repeater. Within Burp Suite, we'll rely heavily on Repeater to discover vulnerabilities. We can also use it to attack web applications, assuming the payload hasn't already been made programmatic via verified exploits. First, let's craft an example to visualize how to send a request to the Repeater tab. We'll start by turning on Intercept and then returning to our browser and navigate to the login page, thus capturing the request. Within the Proxy tab request, we need to right-click and select Send to Repeater, then click on the Repeater tab to view our captured request. Our request is ready to be reviewed and modified. Let's take a moment to familiarize ourselves with this particular tool inside of Burp Suite. On the left side, we'll find the Request panel. This panel contains our captured request for the login endpoint. On the right, we'll notice the Response panel. Currently, the Response panel is empty. The Response panel works much like the View Source functionality of a web browser, except it will include any response headers along with the raw body of the response. This panel will be populated with data after we click the Send button. Repeater allows us to perform targeted changes and manipulations to any HTTP request, send it to a web server, and view the corresponding response. This is a particularly useful tab because it allows us to quickly and effectively test our ideas and payloads in the most minimal way possible. We'll click the Send button and populate the response pane. Next, let's cover the URL decode hotkey combination in Burp Suite. We can use this hotkey after selecting any or all of the text from any encoded HTTP request to quickly decode it into a human-readable format. We'll paste an encoded sample URI string in the Request panel, then highlight it to observe the Inspector tool in action. The output provides the decoded string on the right-hand side. We decoded the string fairly quickly by leveraging the Inspector tool within Repeater. This is a helpful alternative method for decoding a string inside of Burp Suite using a keyboard shortcut. Nmap. Nmap is a free and open-source network scanning tool. It can be used to discover hosts, services, and ports on a particular target machine or on entire network ranges. While this tool is more well known for its network scanning capabilities, we can also combine certain Nmap options or flags with various scripts to retrieve useful information during a web application assessment. Let's get some practice with Nmap to better understand how it works. Our first step is to export our target IP environment variable into the terminal using the export command. Exporting environment variables such as a URL or an endpoint is a good habit to acquire. We can more quickly launch the tools we need if these environment variables are preset. For our first Nmap scan, let's scan port 80 and examine the output. We will provide the -p parameter with a value of 80 to indicate that we're interested in only scanning port 80. Next is the IP parameter, which is our exported IP environment variable. In the output, we notice that port 80 is open and the service or protocol being served using that port is HTTP or web. Next, we'll rerun the same scan, this time adding the -sv flag. This flag is short for service version. Essentially, it instructs Nmap to perform simple banner grabs in an attempt to enumerate the service and service version running on a machine. We'll observe the difference between the output and our initial output. The newest output still lists port 80 as open and corresponds to HTTP. However, we also retrieve the Apache version as well as target operating system information disclosed by the headers of the web server. Nmap scripts. We can now expand our understanding of Nmap and learn more about the Nmap scripting engine. As we will discover, Nmap scripts can be extremely useful during penetration testing. Kali Linux provides a large list of scripts known as NSE scripts. We will inspect some NSE scripts associated with the HTTP protocol, all of which are relatively safe. We can visit the default location for Nmap NSE scripts on Kali Linux to get a clearer idea about the number and types available to us. Let's examine a few specific Nmap NSE scripts targeted at the web. We'll start by running Nmap again using -p to only scan port 80. We will also provide the script argument to run the HTTP enum script, which will search for common directories. Running this basic file and directory discovery script, we found a potentially interesting file and also retrieved the version of WordPress running on the remote machine. With our first Nmap script scan complete, next we'll examine the HTTP methods script. This script determines which HTTP methods are enabled on an HTTP server. It is one of the many NSE scripts that accepts arguments to customize its operation. Let's run Nmap again, this time using the HTTP methods script. We will also pass an argument to the script. In some directories, such as the web root directory, we may only have access to the HTTP methods get, head, post, and options. With the HTTP methods script, we can identify the methods supported by the web server at the URI provided. We can also provide a specific URI using the URL path script argument. The script identified that the get, post, options, and head methods are supported by the web server at the specified URI. Since we know our target is running WordPress, we can also use the WordPress enum nmap nsc script. This script will assist us with enumerating plugins and themes present on the target WordPress machine. We discovered a popular plugin called Akismet, which means that the nmap nsc script is functioning as intended. Choosing a word list. SecLists creates several directories containing a wide variety of word lists that we can use. If we're performing fuzzing, we can use the SecLists fuzzing directory. For password recovery, we can use the word lists in SecLists passwords directory. Becoming familiar with these directories and how they can assist us is vital to our success when assessing web applications. It's worth our time to investigate these lists, make note of the available payloads, and become familiar with them. Building custom word lists. In some scenarios, we may need to develop a custom word list. Let's imagine we're tasked with assessing a web application for the Megacorp1 domain. During our assessment, let's say we encounter a lot of data that the organization has disclosed publicly, information ranging from first and last names of employees to project titles, and even including commonly used organizational abbreviations. We can leverage this data to create custom content using a variety of Kali Linux tools. Let's first examine Cool, a word list generation tool available on Kali Linux. We can use this tool to create custom word lists from content present at a URL we specify. For this example, we'll target Megacorp1. We can tell Cool how far we want it to crawl or spider using the -d parameter. We can also specify the minimum word length we want to be generated for our word list using the -m parameter. Finally, the -w parameter instructs Cool to output the word list at a destination of our choice on our attacking machine. Let's review some of the output. Excellent! We've utilized the content from an endpoint to generate our own word list. Before we conclude this section, let's explore another approach to creating custom word lists, as our word list may not always be generated by a tool such as Cool. Let's suppose instead that we've achieved code execution on a target machine and want to create our own word list. We can develop a word list of executable binaries based on our own machine to create a template. Using this command, we can list out all possible binaries on our Kali Linux VM. Next, we'll use sed to remove the numerical listing of each binary. This provides some helpful output of all the binaries present. However, we will notice a lot of spacing issues. We can use sed to remove any extra spaces. Finally, we can avoid duplicate values by piping all output to sort with a parameter of -u, indicating that we only want unique results. Naturally, we would like to save our output, so we pipe all output to a file. Examining the file, it's clear that we have successfully created a custom word list of Linux binaries we could leverage to enumerate a target system with code execution. This wraps up our custom word list section. There are endless possibilities for creating custom word lists, and understanding how to develop them will often make cracking logins easier. Installing GoBuster and basic usage. Let's run GoBuster using the help flag to begin familiarizing ourselves with the tool's options. Before we review some of these commands and flags, we need to export our environment variables. Let's export a URL environment variable to target with GoBuster. With our environment variable set, we're ready to discover some endpoints using this tool. Endpoint Discovery with GoBuster. Let's practice using GoBuster to discover file and directory endpoints. We'll set dir as our mode for directory and file enumeration, -w for our word list, and -t to run the scan with only 5 threads. We'll also provide the -b parameter for a status code block list so our attempt is not interrupted by redirects. GoBuster scans only a few resources using the word list. This is because we used the -b parameter to block list the response code 301, an HTTP status that typically indicates the requested resource is set as a permanent redirect. This output further confirms the tool's basic utility, which will be essential for us in later sections. In the next learning unit, we'll learn how we can achieve more aggressive results with wfuzz and sec lists. Go bust those subdomains. When performing web assessments and engagements, we may occasionally be presented with an entire domain for scope, depending on the client organization. Let's cover methodologies for subdomain discovery as well for cases with a more targeted scope. An example subdomain for megacorp1.com might be mail.megacorp1.com. During our testing, we can specify this subdomain for testing using the -d parameter. wfuzz. The next tool we'll examine is wfuzz, which can provide excellent coverage for testing input points on the web surface. First, let's cover the term fuzzing. Fuzzing is a technique that involves sending a large amount of both valid and invalid data in the form of input to an application or a service. A fuzzer is a type of automated software that performs this input testing. Let's experiment with fuzzing by targeting web applications and web servers with wfuzz. First, we'll run wfuzz with the help option. Let's cover a few of these options and review some examples using wfuzz on our WordPress lab machine. When we later export our URL environment variable, wfuzz will replace the fuzz keyword in an HTTP request by iterating over our provided word list. The keyword being replaced can be anywhere in the request, including the URL, parameter, headers, or body. Next, we'll use wfuzz to discover directories and files like we did with GoBuster. Then, we'll leverage it for more advanced fuzzing. File discovery. In this section, we'll practice using wfuzz for file discovery on a WordPress lab machine present in the online portal. Before launching any fuzzing attempt, we need to ensure that our URL environment variable is set properly within our terminal using the export command. With our environment variable exported, let's start fuzzing some files in the web root. We'll run wfuzz with -c to display color output, -z to specify the input source, and --HC to avoid non-existent and erroneous responses. After several minutes, our scan will complete and we'll notice that files were discovered. We didn't discover directories because we did not include a trailing forward slash to our environment variable when fuzzing. We'll cover directory discovery more closely in the next section as we further discuss the trailing forward slash and proper usage of sec lists. When properly executed, wfuzz can be very helpful for both directory and file discovery in the early phases of enumeration. Directory discovery. To find directories using wfuzz, let's re-export our environment variable with a trailing forward slash. We'll also update the list we're using in our wfuzz command. Because we specified a trailing forward slash, we received the corresponding directories and response code present in the web root. We also received a 200 OK response for WP content. In the next section, we will discuss using wfuzz for parameter discovery. Parameter discovery. It's not uncommon during early web application enumeration phases to encounter a file returning a 200 OK response. This is a normal, expected response for a remote file that exists on the target web server and has access permissions. We should, however, note an important related topic: parameter discovery. Let's imagine a scenario in which an organization's web developer has created an application that's ready for security testing. During this phase, we would typically perform some penetration testing to ensure that there are no hidden parameters in the web application that could be leveraged maliciously. We'll need to check for hidden parameters on the endpoint. To perform this check, we'll need to review the wfuzz output for any valid response size changes, which would indicate the presence of a hidden parameter. If there are no valid changes in response size, we're in the clear and can expect no potentially hidden parameters. However, we may find such parameters if we perform a parameter discovery attempt using a word list and encounter a change in average response size. Further, we want to make sure when performing parameter discovery that we utilize the best word list we can. For this purpose, we have chosen a word list titled burp parameter names.txt. We indeed found 3 potential hidden parameters. Although these parameters are not directly exploitable in this scenario, we've still learned the process needed to check an endpoint for hidden parameters that might have either been left behind, are not intended for end-user interaction, or serve data processing purposes. Next, we will explore fuzzing a single parameter for preliminary sanitization checks. Fuzzing parameter values. In the following examples, we will practice the basics of fuzzing a single parameter value on a target web application. In this scenario, however, we will be fuzzing the FPV parameter with a common username word list. We quickly notice that there are a lot of erroneous responses with our parameter values, specifically the 301 response code. To exclude these erroneous responses from our wfuzz output, we will update the HC option to include 301. Sure enough, we discover that the FPV parameter returned a different response code and size when the word list reached the Unix keyword. Fuzzing post data. In this section, we're going to discuss how to fuzz post data in an HTTP request. We will also attempt to brute force our way into the WordPress admin page by testing the admin user. Let's begin by intercepting some data to visually demonstrate the post data parameters we're interested in. We can simply navigate to the WordPress login page and attempt to log in. We'll then provide some dummy data to demonstrate our example. We'll observe that both the username and password values we submitted to the login page were captured in transit. The parameter name for the username is log, while the password parameter is pwd. Of course, this is dummy login information to provide visual representation of post data. Next, let's target pwd with wfuzz and try to discover a valid username and password combination. To begin targeting for our brute force attack, we'll provide the -d parameter to specifically fuzz the post data of the endpoint provided. We will also need to supply a value for this to work properly. Finally, let's use the HC parameter with a value of 404 to avoid erroneous responses. In this case, a 404 message indicates a not found response. The output shows that we receive several erroneous response sizes. Let's correct this by supplying the HH parameter to suppress the response size value of 6059 bytes, thus filtering our results so only successful attempts are shown in our output. Great! We have successfully retrieved the very insecure password of password for the admin user via our targeted fuzzing of post data. We've now covered the basics needed to use wfuzz. The methodologies provided in this section should be helpful when working through the labs. HackCrawler and the Wayback Machine. HackCrawler's power lies in its ability to combine spidering techniques with the Wayback Machine, thus providing us with a large list of previously used or archived domains that would otherwise need to be busted via tools like wfuzz or GoBuster. Let's use HackCrawler to target Megacorp1. Let's add our target to a text file, then pipe the file to HackCrawler. HackCrawler provides an abundance of useful information. Essentially, without using domain busting or creating a heavy traffic load, we've managed to obtain previous records of obscure subdomains and expanded our attack surface. Shells. One of the core goals of any cyber attack is to achieve code execution via a shell, regardless of the attack surface. With a shell, we will be able to input our own commands directly from a command line interface or terminal, which the underlying OS will know how to interpret. However, before we retrieve a shell of our own, we will need to experiment with initial code execution. To do this, we'll target the exec sandbox for our example, which is a specially designed lab machine. In this sandbox, we will utilize PHP to execute a system command. To do this, we will make use of PHP's native pass-through function. This function permits code execution and is designed in such a way that output is clean in a web client. Thus, we will pass the ID command to the pass-through function in our live execution sandbox and examine the results. We can execute code through a web technology, in this case, PHP. This particular machine serves a single purpose: code execution through the web. Cross-site scripting, understanding the sandbox. In order to exploit XSS vulnerabilities, we'll need a target user to visit the page we have injected into. To accomplish this, we have access to an XSS sandbox with various vulnerable applications. The application is split into 4 sections. The left side is our hacker side, where we can navigate the various pages and exploit vulnerabilities which get executed in our browser. The right side is the user side. On this side, we can configure the user to conduct various types of actions and, when the render button is clicked, have the user visit the same page we are visiting. Let's break up each side further. First, let's investigate the top left navigation bar. The navigation pane has links to various vulnerable applications. We'll use these various applications in our examples later, and some will be left as exercises. The pages are displayed in the lower left quadrant of the page. We'll call this our hacker browser. Currently, we are on the info page. This section displays the page in an imitation browser. This side of the page is using our current browser to render the content. That means that if we were to exploit a XSS vulnerability on one of the vulnerable applications, we would be exploiting our browser. Once we have the exploit ready, we can use the control panel found on the top right quadrant to render the page. When a page is not being rendered, we can use the control panel to configure the simulated browser and its actions. Clicking the Render button will make the simulated user browser load the page currently loaded in our hacker browser. Once rendered, a screenshot of the user's browser will be sent back to us. We can disable these screenshots by unchecking the Refresh Screenshot checkbox. The rendered page will be displayed in the lower right quadrant. The navigation buttons within the target browser are intentionally not under our control because we are simulating a remote user. If we clear the render by clicking the Clear button in the control panel, we can go back to change the settings. Let's check the Used Stored Password checkbox to simulate a user with a password stored in their password manager. Once checked, we can click Render again and find that the user's browser filled in the credentials. Being that this site is not vulnerable to XSS, we have no way of knowing what the value of the password is. However, as we'll find in the other applications, we have ways of exfiltrating passwords. In order to inject JavaScript, we must first understand what JavaScript is, what it can do, and some fundamentals that will help us when exploiting XSS. Syntax overview. Let's review a JavaScript function that processes some data and logs it to the console. In this code, we find a declaration of a function named processData. A function is a series of statements. Typically, a function may accept some arguments, accomplish a specified task, and then, if needed, return the processed data. Next, we find the declaration of an object saved into the foo variable. A variable stores a value. This could be a string like hello world, an array, an object, or a number of other property types. On line 15, we find the calling of the process data function using the foo variable as an argument. An object contains key value pairs called properties. The foo object contains a single key, which is set to an array of strings. Functions can also be properties in objects. In these situations, the function is called a method. We'll use the term method in this topic to use the accurate terminology. Now that we understand the declared items, let's review the contents of the process data function to understand how it works. On line 2, a loop begins with each item in the data.items array. On line 3, each line will be logged to the console. To understand what the console is, we need to understand how we can execute JavaScript. Being that JavaScript was initially designed to be run in a client's browser, the best debugging tool is actually the browser. We can open the developer tools on any page. However, some pages might have libraries loaded that change the default behavior of an application. For this reason, we will use the blank page in Firefox. Here, we'll click on the hamburger icon in the top right, click Web Developer, and finally, click on Web Console. Before we can paste anything into a Firefox web console, we must first type allow pasting or else an error will be displayed, reminding us to do so. This security mechanism prevents users from running untrusted code and being phished. Remember, if we can get a victim's browser to execute JavaScript, we can access almost everything on that page. When we paste the code and press Enter, the code is executed and the console logs 3 string outputs. How did the browser know to log the output when we never defined what console.log is supposed to do? Our code executes because console.log is a built-in method within the console API provided by the browser. We have access to many useful web APIs if we're exploiting a vulnerability we can inject JavaScript into. Useful APIs. The window API represents the window in which the document lives. In addition to the properties, the window API also provides us with access to the alert method. This method is very commonly used to demonstrate that an application is vulnerable to XSS. Let's try to run the alert method in our console. We'll pass in a string to be the content that will be displayed. While alert might be the most common method used to prove an XSS vulnerability, the most effective API for actually exploiting an application vulnerable to XSS is the document API. The document API allows us to interface with the DOM, which contains every part of the page loaded in the user's browser, including all text and password inputs, cookies, and even key press events. To interface with the document API, we'll need a page with more content. We'll use the info application for this. We'll start by navigating to the page. Let's extract the value out of the username and password input boxes. We'll first have to query for the input boxes. We'll use the getElementsByTagName method, which will return an array of all elements that match a given tag. In HTML, text boxes are created using the input tag. This will be the argument we pass into the method. We'll save the returned array into a variable called inputs. Next, we'll loop through the elements in the inputs variable and extract their value. The for loop sets an input variable for each item in the inputs array and logs the value using each input. However, since the inputs are empty, we get empty string as the response. Let's refresh the page, enter values in the fields, enter our JavaScript into the console again, and review the output. This time, the values of the input boxes were extracted. Even though the password is obscured, JavaScript has access to the text value. While we're capturing our own credentials here, this would be very useful if we can execute JavaScript in another user's browser. Another useful API is the ability to add an event listener for every key press. This can be used to snoop on a victim's messages and credentials. Adding an event listener is done with the addEventListener method. It accepts an event code and a function on how to handle the event. Let's first create a function that will log key presses to the console. In this code, we defined a function named logKey that accepts an event sent by the event listener. The function logs to the console which key was pressed as part of the event. With the function complete, all that's left is to add the event listener and pass it our function. We won't add the parentheses as they will execute the function and pass in its returned value, which is nothing in this case. Instead, we pass the logKey variable, which holds the function. The event listener will execute the function each time a key is pressed. Now when we type anywhere on the document, we can find the keys logged in the console. However, capturing our own key presses isn't very useful, so instead, we want to try to capture other users' keystrokes. For this reason, we've created the eval application within the XSS sandbox. Any JavaScript entered here will be executed by the victim when we render. Let's take our keylogger and send it to the user. We'll paste our payload into the code block within the hacker browser. We'll check only the Simulate Keystrokes option and then click Render. The victim rendered the page, but nothing happened. This is because we're only logging the keystrokes to the console and we don't have access to the victim's browser console. We're going to need to find a way to exfiltrate their keystrokes. This is where the Fetch API comes in handy. The Fetch API allows us to have the user's browser make network requests for remote resources. The Fetch API call is non-blocking, which means that the UI will not be locked up while the request is made and the response is returned. This also means that Fetch doesn't return the data immediately, and instead, it returns a promise to complete the execution. If we need to access the response, we use the then method and pass in a function to execute when the response is available. However, we don't always need the response. For example, we can use it as a way to exfiltrate data from the user's browser to our Kali machine. As long as the request is sent to our server, we don't need to handle the response in the user's browser. Let's start a Python HTTP listener on Kali to log requests to the terminal. Now we'll go back to using the console window and a blank tab and make an HTTP call to our Kali IP using fetch. We receive an error stating that the same origin policy disallows reading the remote resource. However, if we check the Python server logs, we find that we received a request. The log contains the URL that we queried for. Let's go back to our keylogging payload and review what we can change to exfiltrate the key presses. The problem we ran into with the payload was that console log doesn't exfiltrate data. Let's replace this line with fetch and use the eval application to have the victim execute our code. We'll change the console log line to run fetch. This will make an HTTP request to our Kali machine and include the key pressed. Let's type this into the eval application and render with the Simulate Keystrokes option checked in the XSS sandbox. From the user's perspective, nothing is happening. However, if we check the logs, we'll find a message that the user is typing. Excellent. We find a message that the user is typing on the page. Reflected Server XSS. Reflected Server XSS is often found in locations where user input is sent via GET parameters. To exploit it, we would typically send a link to a user with the payload. Since the user trusts the domain, they'll click the link, the server will append our payload, and the user's browser will execute the payload. It's possible for post parameters to also result in reflected XSS. However, we wouldn't be able to fish a user via a link. Instead, we would have to fish the user to a site we control and have a form auto-post when a user visits. For this reason, we'll be focusing on reflected XSS vulnerabilities via GET parameters. For most of this section, we'll use Firefox to discover the vulnerability and build the payload. We'll use the search application found on the XSS sandbox. The home page contains a single input box we can use to search for a term. Let's search for OffSec. This search engine isn't very useful. In addition to the search term being added to the S parameter, we notice that it was also appended to the search page HTML. Let's inspect this in the DOM to understand how it was appended to the document. We'll select the search term, right-click, and click Inspect Element. We find here that the keyword was injected into a div element. If the S parameter is vulnerable to XSS, we won't have to escape out of any existing HTML tags. A good place to start with XSS testing is to first attempt HTML injection. HTML injection has less potential for error, so it's a great control for our testing. Being able to inject HTML doesn't always mean that we can inject JavaScript, but it's a great indicator. Let's try to search for OffSec between H1 tags and review the response to determine if the HTML was rendered. When we searched for a term with HTML, the HTML was rendered instead of escaped. This most likely means that we'll be able to inject JavaScript as well. Let's try this. We will use the standard alert function to validate the proof of concept works. We've successfully injected JavaScript into our own browser. Now let's click on OK to dismiss the alert. If we inspect the URL, we will find the encoded version of our payload. Next, let's click Render on the XSS sandbox to have the victim render the page as well. The URL is the same URL containing the encoded payload that the victim will be visiting. Normally, this would be sent through an email, chat message, or a link on another site. When the target user renders the page, we find an alert box is displayed. This means we've successfully injected an XSS payload to our target. Now, let's exploit this in Burp Suite to confirm the server is appending the payload. If we send a request to the server and our payload is included in the response, we know that this is a reflected server XSS. We'll begin by visiting the Proxy tab. Let's disable Intercept by clicking Intercept is on. Next, we'll open the embedded Chromium browser. In the browser, we'll navigate to the same search page on the XSS sandbox. Let's submit our payload in the search bar again to capture the request in the proxy history. When we submit the payload, we should exploit ourselves and receive the pop-up dialog. This time, let's open the proxy history and find the request we just sent with the response. If we scroll down on the Response tab, we can indeed find that our payload was reflected directly in the content. With this discovery, we can confirm that the server initiated the appending of our payload to the document. Stored Server XSS. Unlike reflected XSS, stored XSS does not require us to send a specially crafted link. Instead, any user that visits the vulnerable page rendering the stored XSS will execute the payload. Because of this, we don't have to worry about limiting our payload to GET requests. For this example, we'll use the blog application found on the XSS sandbox. At the bottom of the page, we find that the application allows us to post a comment. Let's post a comment and check how the application responds. We'll inspect the HTML by right-clicking on the username. We find that the name and comment were added. Let's try to inject an h1 tag into the comment and review the output. If the HTML is rendered, then we can move on and try to inject JavaScript. We'll set the same username, offsec, but set the comment to hello between h1 tags again. Instead of getting a big hello, the HTML tag was not rendered. Let's inspect the element to understand what's going on. Strange. We seem to be showing HTML tags. Why isn't this rendering? To find the answer, let's right-click on the element and click Edit as HTML. Now when we review the output, we discover what's going on. The server seems to have encoded the HTML characters. Unfortunately, this most likely means this parameter is not vulnerable. Let's try the username parameter. We'll visit Reset in our hacker browser to clean the database first. We'll use the same payload for the username. After the comment is submitted, we find that the h1 HTML tag we injected is rendered. Now that we know we can inject HTML, let's attempt to inject JavaScript. We'll use the alert function since it will give us a clear indicator that the XSS was executed. We'll use the same alert payload as before. However, since the HTML will be rendered as the username, it will be very clear to the administrator which comment contains the exploit. Instead, we'll attempt to be a bit sneakier by prepending the name John to the payload. This way, the username field won't be empty once everything is rendered. When we submit the payload, we execute the injected XSS directly in our browser first, so an alert box with 0 is displayed. Once we close the alert, we can render the payload in the target user browser by clicking Render in the control panel. Interestingly, we find that no specially crafted link is required to exploit the vulnerability. Any user visiting this page will receive an alert box. Reflected Client XSS. While the impact for Client XSS is mostly the same as Server XSS, the discovery and payload may differ. Since the payload is appended on the client side rather than the server side, there is a layer of abstraction that we have to handle. Unlike Server XSS, we cannot discover Client XSS by reviewing the requests and response. Instead, we need to have a browser render the page fully to discover if the payload worked. Since the payload is added to the content by the client, we can also discover Client XSS vulnerabilities by reviewing the client JavaScript. We'll quickly review the code to confirm the vulnerability, but deep source code review is out of scope for this section. The target will be this survey application in the XSS sandbox. When we visit the page, we notice that the name of the user is provided in the name query parameter. This name is also reflected on the page for the welcome message. Let's wrap the name in h1 tags to find if we can inject HTML. Our browser will automatically encode the parameter before it sends the request. The HTML is rendered and the name is now in bold. Let's use Firefox Network Tools to review the raw response so we can confirm that this is indeed a client XSS. To do this, we'll open the network utility through the Web Developer menu. If we click the reload icon on our hacker browser, we can force Firefox to send the request again to our target server. We'll find the request listed in the Network tool. If we click the request, we'll open yet another window pane with multiple tabs. One of the tabs is Response, which contains the raw response that the server sent. However, if we click the Response tab, Firefox will attempt to render a preview of the HTML without any JavaScript. We'll close this pane by clicking on Preview. From here, we can find that the original welcome message simply said, "Welcome, user." This isn't what's being rendered on our end. Where could our payload be rendered? In the left-hand window, we find additional resources loaded on this page. The CSS pages probably don't have any logic that changes the welcome messages. The jQuery file contains an external library. Finally, survey.js seems to be custom to this application. We might find a clue in this file. One of the first things this JavaScript file does is set the inner HTML of the welcome DOM element to the value set in the name query parameter. This is where we are injecting our HTML. Next, let's try to inject an XSS payload. We'll start with our standard alert payload. The page loads, but the payload does not execute. The name in the welcome message is blank as well. Let's investigate to understand what might be going on. We'll have to expand the p tag to show the contents of the message. From this viewpoint, it seems that our injection was appended appropriately. The inner HTML documentation specifies that a script tag inserted with inner HTML should not execute. However, there are ways to execute JavaScript without using script elements. Let's give this a try in the survey application. Excellent. We were able to exploit a client XSS. Stored client XSS. Unlike reflected client XSS, stored client XSS does not require an attacker to send a specially crafted URL to a victim. Instead, any user that visits the vulnerable page will automatically be exploited. We'll again use the survey application in the XSS sandbox with Firefox to test this. Let's use the application as intended and submit the survey as the default user, Jason. We'll enter the user's age, city, and the remaining questions. At the end, we're taken to a page that shows the summary of our answers. On this page, we find that a new query parameter was added. If we refresh the page, we also find that the user's results display. If we remove the result query parameter and visit the page, we are taken back to the user's result page again. It seems that the application only allows us to submit a survey once for a username. If the survey has been submitted, it shows the answers. Let's change the name and submit the survey. This time, we'll answer one of the questions with HTML. We'll set the payload on the question that reads, "Where are you from?" When the result is displayed, we'll find that the HTML tag was rendered. If we review the source code of survey.js, we'll find that this result table was added via client JavaScript and not the server. However, unlike with the reflected XSS, the data was added via append. Let's try our standard alert payload again and review the output. Again, we'll set the payload at the same question. When we answer the remaining questions, we get an alert box on the result page. If we click past the alert box and reload the page, the alert box is displayed again. Let's render the page in the victim's browser to confirm that the payload works. Since this is a stored XSS, the URL does not require any special payload. Excellent. We have now exploited stored client XSS in a victim's browser. Moving the payload to an external resource. The following exploits we discuss will be more complicated than an alert box. For this reason, we need to use a payload that can deliver a more complicated exploit. While it is possible to write a single-line exploit to inject into the application, it's better to inject an HTML script tag, which loads the full JavaScript from our Kali machine, as it will let us write more complicated JavaScript without encoding. Let's demonstrate this by exploiting the search application in the XSS sandbox. For now, we'll stick to the alert exploit, but this will be updated in the upcoming sections. Instead of using inline JavaScript, we'll add a script tag and set the src attribute to a file hosted on our Kali machine. This will make the payload as follows. We'll also need to make a JavaScript file called XSS on our Kali machine and host it. We'll use Python's built-in HTTP server to host the file. We'll serve everything in a directory named XSS, which we'll create in our home directory. Our file will only contain an alert instruction. Finally, we'll start the HTTP server. Now that the server is started, let's use the payload to exploit the search application. The payload will append a script element to the HTML document, and the script tag will load the XSS file from our Kali machine. Let's submit the search and exploit the XSS. When the page loads, the XSS payload is downloaded and exploited. Let's click Render to have the victim's browser load this page too. Again, we find that an alert box is displayed. Let's check our HTTP server logs. We find two entries in the HTTP server logs. The first is from our own Kali IP when we loaded the page ourselves. The second is from the victim's browser. We'll use the script element payload and the search application for the remainder of the exploits. However, this payload can be used for any other XSS styles that won't automatically execute JavaScript. For example, client XSS vulnerabilities that use inner HTML. Fortunately, there are other methods to get around this restriction. Stealing session cookies. The age-old goal of cross-site scripting has always been to exfiltrate the user's session cookie. When obtained, we can use the session cookie to authenticate to the application as the victim, but the increased use of the HTTP-only attribute has made this exploit less prevalent. However, it is still important for us to understand how the exploit works and how an application responds when the HTTP-only attribute is set. Using JavaScript, we can access the cookies of a page using the document.cookie property. We'll extract this value, URL encode it, and use fetch to send it back to our Kali VM. All of this will be done in the XSS file. We have edited the XSS file to extract and encode the cookie and send a GET request back to our Kali VM with the encoded value. We'll paste the script payload into the search application and submit the payload. Again, we'll exploit ourselves, but since we don't have cookies set, the log in our HTTP server will be empty. We can safely ignore the 404 error correctly stating that the exfil file doesn't exist because finding this log means that the data was exfiltrated. Next, let's have the victim run this page. This time, we'll check the box titled Use Non-HTTP Only Cookie and then click Render. The page loads normally, but if we check our HTTP log, we can find a cookie value that was exfiltrated. Excellent! Let's uncheck the Use Non-HTTP Only cookie and check Use HTTP Only cookie instead. When we click Render, the page loads normally again, but if we check the log, we don't find a cookie. When a cookie is set with the HTTP only flag, JavaScript cannot access it, so we can't exfiltrate its value. Stealing local secrets. Web applications have the ability to store data in a user's browser, a feature typically used to store larger amounts of data. For example, an application that lets us edit documents might store the document locally in the browser as a cache before it's sent to the server to be saved. This ensures that even if the user closes the tab, they don't lose their data. However, local storage might also contain secrets like API keys or personal user information. There are two types of storage available to us: session storage and local storage. The only difference between the two is the level of persistence. While local storage will keep the data until explicitly deleted, session storage will keep the data until the tab is closed. The local storage data can be accessed by using the window.localStorage property, while session storage can be accessed with window.sessionStorage. To exfiltrate local storage, we'll convert the object into a string, URL encode the string, and use fetch to send the data back to us. We'll use the search application in the XSS sandbox to load the XSS file and execute our payload. When the payload loads in our browser, we'll receive a log containing keys used to run the XSS sandbox. However, we're targeting our own browser here. Instead, let's check the Data in Local Storage checkbox and render the page in the victim's browser. If we check our HTTP log, we should find an entry with the contents of the victim's local storage. Excellent! While we only showed local storage in this example, session storage could also be exfiltrated using the same technique. Keylogging. At times, attacking the application might not be the best course of action. If the user of the site is the larger target, it might be better to target the user instead. Keylogging is one of the best cross-site scripting methods to target users with, as it's very difficult for a user to detect, but very effective in exfiltrating secrets. Keylogging with XSS is limited, though. We are able to keylog by creating an event listener for any keystroke, but it can only be set on the current document. That means if the user is on a different tab or in a different application, we won't be able to intercept their keystrokes. However, if the user is typing a private message or attempting to log in on our target site, we can capture those events. The JavaScript event for key presses is keyDown, which will be passed into the addEventListener function. This function also accepts a callback function to run for each keyDown event. Within this function, we'll send the key that was pressed back to our server. Once the file is saved, We'll check Simulate Keystrokes and click Render. When the page renders in the victim's browser, we'll receive the message they are typing into our HTTP log. As the user types, we receive each keystroke. If we put the message together, we find that the user was searching for divorce lawyer near me. Maybe not something they wanted others to know just yet.